This is example 3.7. We're going to look at another example here of the interplay between kinetic energy and potential energy. Okay. A 40-kilogram girl slides down a playground slide that's 5 meters long and its top is 2 meters above its lowest point. Her speed is 4 meters per second down at the bottom. How much energy was lost to friction? And how much force, or with how much force, did the friction slow her down? So if you've ever gone down a slide, you recognize that you go down maybe fast, maybe slow. It depends on the friction, right? The friction applies a force that is the opposite of the motion of your direction, right? You're going down, the friction acts as a force in the opposite direction, and that slows you down, okay? So if you were just to jump off the slide, you would end up hitting the ground faster than you would if you went down the slide, right? So that friction is slowing you down, and we need that friction so that we don't get hurt. So let's figure out what the potential energy is. The potential energy is just mgh, right? The mass times the gravitational acceleration times the height. Well, the slide is 2 meters high. So when you're up here at the top, you're 2 meters above the ground. G is the gravitational acceleration, that's constant. And the mass, well, that's given, that's 40 kilograms. So let's calculate how much potential energy that girl has as she prepares to do this slide. Okay, so we essentially have 40 times 2, which is 80, times 9.8, 784, it looks like to me. 784. Now, remember the units? Kilogram, meters times meters, that's meters squared, divided by seconds squared. That's the same thing as joules, right? A kilogram, meters squared per second squared, we call that a joule. Okay. Remember, a Newton is a kilogram meter per second squared. Okay. And acceleration would be meters per second squared. And velocity or speed is just meters per second. So this is acceleration. Okay. So that's how much potential energy is. So if the girl just sort of jumped off the top of the slide or fell off the slide here and hit the ground, the amount of kinetic energy that she would have at the end would be equal to this amount, 784 joules. But let's see what happens with the slide. They measure the speed at the bottom. That's your final velocity. So the kinetic energy at the bottom of the slide is just 1/2 mv final squared, right? At the bottom of the slide. At the top of the slide, the velocity is 0, so the kinetic energy is 0. So that would be 1/2 times 40 kilograms times 4 meters per second quantity squared, 1/2 mv squared. So that's 20 times 16, which is 320 joules. So look what happened. Again, kilogram meters squared per second squared. That's a joule. Look what happened. We lost some energy there, right? There's a difference in energy. And that's the potential energy minus the kinetic energy. It looks like it's 784 joules minus 320 joules, which is 454 joules. Where did it go? Where did that energy go? It went into the friction. It's actually going to heat up your bottom, right? Your butt's going to get warmer. So is the air around it, and so is that metal. It's going to get a little bit hotter because of the friction. It's converted into heat, okay? So that's our essentially what happens then. So now what we can do is we can say that the potential energy minus the kinetic energy is just your frictional energy. So I'll just write that as E friction. Sometimes people call it a type of work. So we could call it frictional work. Doesn't matter, whichever you want to call it. But we know the value is 454 joules. Okay. Now, the second thing they ask is how much force did the friction slow her down with? With how much force did friction slow her down? Well, again, you're going down this way due to gravity. Friction is moving, friction is applying a force in the opposite direction. I know that's hard to read there. This is an F for force, and then F-R-I-C-T for friction. So it's applying a force. So what you do then is you say, okay, well, our frictional work is equal to the force of friction times the distance, right? That's a formula from way back in the beginning of the chapter, right? It was one of our first equations. So if we want to know what the force of friction is, we just take the work of the friction, divide that by d. So F is equal to W over d. And the d that we're talking about here is not the 2 meters. That's what gives you the potential energy. It's the friction due to the slide. So that's 5 meters. So it's 454 joules divided by 5 meters. Okay? Joules per meter is the same thing as a Newton. Not obvious, but it turns out to be the same. 454 divided by 5. 90, I get about 90.8. Oops, let me try that again. 454 divided by 5. I get about 90.8. I'm off a little bit from the textbook there. Let me just make sure. Oh, I'm sorry, I made a mistake here. This is 464. See, I caught my little mistake there. It's 464. My subtraction was bad. 8 minus 2 is 6. It's 464. So 464 divided by 5 is 92.8. Okay, now that's not a typical way that we would write units for force. So how would we deal with that? Well, we would say that 92.8 joules per meter is essentially a kilogram meters squared per second squared divided by a meter. So one of those meters is gone there and that one's gone there. So that gives you kilogram times meter per second squared. That's the same thing as a Newton, right? So 92.8 newtons. And there's your answer.